Hello. With the news buzzing around about the discovery of 3I/Atlas, the question becomes, what makes this new celestial body unique? By comparison, what does a local comet look like, one that is a member of our own solar system? Could this new visitor be part of a larger system of such objects? Let's explore the life cycle of a local comet, and then how different systems of comets form, so that as more discoveries are made concerning this interstellar interloper, we're armed with a clear understanding of these astronomical objects so that we can differentiate reality from clickbait. What are the implications of this new field of study? I'd like to raise the question, is this humanity's first encounter with an entity of this kind? Could future discoveries explain forgotten pieces of humanity's past, or provide insight into our own future? Join me on this episode of Squaring the Circle as we ponder these questions and dive into everything you need to know about comets to have an informed opinion about 3I/Atlas. Greetings, I'm Randall Carlson, and I'd like to welcome you to another episode of Squaring the Circle. In this edition of Squaring the Circle, we're going to take a further examination into some of the features and unexplained questions of what we assume at this point is Comet 3I/Atlas, and 3I, 3 is because it's the third interloper that we've now discovered within the past 10 years. And we're going to look at that in the context of what we know about comets in general from what we've learned about our own local system of comets, both short period and long period comets. You're going to learn what those are and what the differences are. And then we'll have a context for trying to get a clearer picture of what this thing, 3I/Atlas, actually is. But to embark on that discussion, I would like to welcome my colleague and friend, John Arthur Fiallo. Thanks for joining me tonight.
Howdy,
Randall. It is
Randall.
night here. I don't know if you're going to be watching this, it'll be night, but it is night here, and we are recording this episode of Squaring the Circle.
Nice and late.
Nice and late, yes. Just it shows our commitment to getting these episodes out on a regular basis, even though I should be taking a nap at this point, a nice 7 or 8 hour nap. No, wait a minute, that doesn't qualify as a nap, does it? I think by definition, a nap must be much more truncated than 7 or 8 hours.
Someone in the comment section will give us the scientific definition of a nap. So I'll be reading.
Okay, good.
I'll be looking for
important.
it.
So,
tell us what a nap is. Is it less than 3 hours? I don't know. We'll find out.
I think it would need to be less than 3 hours.
Tell us in the comments section what a nap is. A cat nap, is there a difference?
Oh, a cat nap. Now that's...
I've never pondered the link.
Immediately, when you say cat, you know what I immediately think of. The Leonids.
Now that was a segue.
Somehow, I think you were pulling that up out of the subconscious, the depths of your subconscious. And as a result of that, it reminded me of the Leonids, which we might even talk about tonight if we get time, or if we don't, we'll roll it over into the next episode. Why? Because next month, no, not next month, but coming up soon, we're heading into the fall cycle of meteor showers. And the two biggies are going to be the Taurid shower, which is going to peak right around Halloween, and the Leonid shower, which is going to peak right around November 17th. A few days before, a few days after. Some meteor showers, like the Taurids, literally take about 2 weeks for the Earth to entirely cross the stream. Other streams are much narrower. We're going to talk about that. So I think we should just get right underway and get with the program here and get going into discussing comets, what we know about comets. What do you think?
I agree.
We'll start with the definition. How about that? It's always a good place to start. I mean, the whole edifice of geometry starts with some definitions, right? Everything builds up on definitions.
Always define your terms.
Yeah, always define your terms. So a comet is a celestial body moving about the sun in an elongated orbit, usually consisting of a central mass, which is the nucleus, surrounded by a misty envelope, the coma, which extends into a stream, which is the tail, in the direction away from the sun. And in the animations that you prepared for us, John, we're going to get to see that very explicitly. And it's a very cool thing to see. The term comet comes from the Middle English, taken from the Latin, from the stem of cometa or cometa, which is taken from the Greek, a modification of cometes, which literally means long-haired. So the Greeks would see comets in the sky, and they would envision a long-haired, the tail is forming a long tail of hair, following in the wake of a comet. So that's what it literally means. And you probably haven't thought about this, but if I could zoom in, let's say right here after literally, I always find it interesting, and this is sort of as a student of linguistics and origins of language and so on, the comma that you put in have you ever noticed how it looks like a little cometary nucleus with a tail?
Yes,
streaming behind it?
Yeah.
A little coincidence with no meaning whatsoever, other than it is called a comma, right? So who decided to name this little thing that caused, what does a comma do? It causes an interruption in a sentence, doesn't it? That's kind of an interesting that its role in language is kind of in a way reflecting a role of a comet interrupting the flow of life on Earth. So the point here, people listening to this, is now every time you see a comma, I want you to think about comets. It's right in there to remind you to think about comets. The Oort cloud and the Kuiper disk, and I don't have the source of this graphic. I found it years ago. I always like to give sources, and if we find it, we can include it as a note or something. But here we go in some of the nomenclature connected with comets. We have the Oort cloud of Jan Oort, who was a Dutch astronomer who first theorized the existence of an Oort cloud. And subsequent discoveries have pretty much demonstrated that his theorizing was pretty accurate, because given the number of comets we have found in the zone of the Oort cloud would suggest that, because we've only looked at very small increments of space, but yet we still find comets. So when you multiply that you integrate that over the whole area of the sphere, you come up with a whole lot of comets. So it looks like if there was no reality to the Oort cloud, we wouldn't necessarily look at that zone reaching well outside astronomical units beyond the orbit of Neptune and find any comets at all. But the fact that we're finding them out there suggests that Oort's original model is probably correct. Same goes with the Kuiper disk, and that was Gerard Kuiper. Was he not also Dutch? I can't remember. Yeah, look that up, John. I've got two more graphics here that I've pulled off the internet, and I think by looking at these graphics, you can get a pretty good picture of what this whole cometary system looks like. This is really cool. This is a graphic by Ralph Myers at RLM42. I hope that he doesn't mind us showing off his great artwork here that he put together. I might want to check and see what else he's done. But this is a shout out to him, and he's done an incredible job here of depicting the Kuiper disk inside the spherical Oort cloud. And he's included, look at here, here's some comets that you can see up in the Oort cloud that have been activated by whatever force. We can discuss that. We were discussing that leading up to the show about what it is, what are the possible causes of comets out there in the Oort cloud becoming dislodged. Down here you can see the solar system, and you can see here that the zone of comets goes considerably beyond the realm of the planets. And then this is from starwalk.space/gallery/images. This one really is pretty interesting. You see the sphere, and you can see how it grades into the disk, the Kuiper disk. And then down here at the very center, you have the solar system, the realm of the planets.
When I do my research, whether it's ancient history, cataclysms, or unexplained anomalies, I rely on the best tools available. Just like I wouldn't head into the Channel Scablands without the right gear, or without clothes for that matter, I no longer venture onto the internet without one essential tool: ExpressVPN. Most people don't realize how exposed they are online. When you browse the internet, your activity can leave tracks, just like footprints in the sand in Bruno Canyon. That data can be harvested, sold, and used by advertisers, big tech companies, or even malicious actors. ExpressVPN shields your internet traffic, encrypts your data, and keeps your browsing private. This keeps your ISP from tracking your browsing habits. It also keeps your connection secure from hackers when you're on unprotected Wi-Fi networks, like at the airport or your favorite coffee shop. ExpressVPN has partnered with us to support this show, and they're offering my viewers 4 months free when you sign up at expressvpn.com/Randall. So if you'd like to support the work we do here and protect your data at the same time, then it's expressvpn.com/Randall, where you'll have 4 months free. So thank you, and now let's get back to the show.
So you have to start thinking, when I was a kid coming up, the solar system ended with Pluto, pretty much. Now Pluto, it's not a planet, a recognized planet anymore. But in order to, an accurate picture of the solar system now has to include the whole system here. Then, once we start getting into, which would be a very interesting thing to explore in upcoming episodes, when we start getting into the idea of cosmic life, the term?
Exobiology.
Thank you. Exobiology. That's the one I was looking for. The idea that life perhaps originated out there in the cosmos, and the precursors of primordial life delivered to Earth via comets. That's, to me, an extremely fascinating idea. Then it goes even further. It's been referred to as panspermia, the idea, the distribution of the seeds of life. And who was it? Was it Fred Hoyle even who took it to the next level and actually dared to talk about directed panspermia? But what does that mean? I think we'd better not go there tonight, but that's kind of brings us into the realm of theology. And I, for one, over our many opportunities to discuss the deeper aspects of our existence, I am not adverse to discussing subjects like directed panspermia and what that would actually mean or imply.
Francis Crick was the
right, of course, discoverer of the DNA. Francis Crick. Yep. How could I have forgotten?
Along with Leslie Orgel.
Francis Crick. Wow. Well, there we go. So there's the. I think we can get a pretty good idea of the whole structure of the solar system. And really, once you get to the outer zone of the Oort cloud, you're getting perilously close to being halfway to some of the nearest star systems. So, anyways, we're going to skip the next 4 or 5 slides. We may come back to it because it has to do with the unique geometry of the solar system, the architecture of the solar system, and its appropriateness for delivery of cometary care packages, if you will, to the inner solar system. So we may circle back to that if we have time. Otherwise, we will save it for probably the next episode. All right, a little more nomenclature for us. We have the trail, which is actually dust, right? And then we have the tail. And it's the tail. Now, either one of these tends to point away from the sun, particularly if the dust is a very fine grade of dust. It can be, the question is can it be directed by the pressure of the solar wind, which is moving radially out from the sun. So we've got the nucleus of the comet, which is also the coma. This is a photograph of Comet Hale-Bopp, and I believe in a minute you're going to be able to pull up and we're going to be able to see the orbit of Comet Hale-Bopp, right, which was discovered, well, we'll get back to that when we pull that up. All right, so that takes us up to this, the 5 stages in the life cycle of a comet. So number 1, aggregation. What does aggregation mean? If we look at
aggregate means multiple small things that have formed a whole. So aggregation would be the formation of multiple small things, creating a whole.
Yeah, pretty much. Then we have hibernation.
Dormancy.
Dormancy, yes. Activation. Well, that's your waking the bear up from its long sleep out in the Kuiper disk or the Oort cloud. Right, where it's basically in the cold depths of space. The temperature of these things are probably close to absolute zero, right? So
yeah, I was reading 3 Kelvin, 8 Kelvin, somewhere in there for some of these.
That's really, really cold, isn't it?
Cold.
Very cold. So activation. Now, of course, that raises the question, what triggers the activation? We'll come back to that. Disintegration. Right, obviously what that is. We've just been seeing the examples. And then finally, amalgamation. What is do you have a definition there for amalgamation?
The process of uniting or merging 2 or more things.
The final stage. Because ultimately what happens?
2 things become one. It hits the moon. It hits June. Hits Jupiter. It hits something.
Yeah, and even if it disintegrates into dust, that dust is ultimately being swept up by prime candidate, the sun, second Jupiter, but theoretically any object that crosses in its orbit will eventually sweep up that dust. Otherwise, there would be so much dust up there that, we couldn't see anything anymore. It's because the dust is being swallowed up by the sun and Jupiter and the rest of the planets. Okay, so that's the amalgamation. Now we can break it down a little further. So aggregation is the accretion of the interstellar matter that we would say is left over from and this is most of the scientific models, is that the formation, the construction of the inner solar system took place first, followed by the gaseous giants, and then whatever was not utilized in the creation of the sun and its family of planets was exiled to the outer regions of the solar system.
If you assume this model, then what we're seeing outgas from 3i Atlas, and you assume that 3i Atlas is natural. This aggregation point, again, assuming that model, assuming 3i Atlas is a natural formation, this tells us something about the star system from which 3i Atlas hails. So what does it tell us? I'm not entirely sure. High nickel carbonyl, high CO2 to H2O.
Mm-hmm.
Very unusual. Doesn't fit any of the models that we have currently. But like you said, there's some very volatile models of the inner Milky Way.
Mm-hmm. Mm-hmm.
Very violent and very interesting place.
Could this object be thrown out from the inner reaches of the Milky Way? I don't know. It's interesting, and I want to know more. So, aggregation consists of the accretion of interstellar matter, condensation, right? Integration, meaning these pieces are integrating, and then ejection from the inner solar system, primarily a function of Jupiter. To me, the very appropriate biblical metaphor that I like as a builder is that this stone the builders rejected in the formation of the world system. And then reservoir formation, the Kuiper disk, the Oort cloud. Now, of course, this is conjectural, so don't somebody come in here and saying, oh, we're definitively saying it's this and it's that and it's this. That's not what we're doing. We're creating conjectural models here that seem to be consistent with what we know, the evidence, okay? We are allowed to do this, okay? Then hibernation. Once it's out there in the reservoir, it hibernates in the deep cosmic winter of interstellar space. In the Oort cloud or the Kuiper disk, you just said temperatures as low as 8 degrees Kelvin. So that is really, really cold. So these things, they get frozen. They're in this large system, slow orbiting about the sun. It would appear that the system is rotating on some kind of an axis, but very slowly. Then you have activation, perturbation. Something perturbs them, which causes the comets in this quasi-stable orbit to become dislodged. If they're accelerated, they tend to move out away from the sun. If they're decelerated, they tend to migrate in towards the sun. Now we get the potential of orbital transfer, and we'll come back to that because orbital transfer means transferring into the orbit of Neptune, the outermost large gaseous planet, which can now exert very pronounced gravitational effects on any cometary object which comes within its zone of influence. Not within the Roche limit necessarily, but within its gravitational zone of influence. So we have orbital transfer, which then sets up the sunward journey. As it approaches the sun, we start getting outgassing. It heats up as it moves in through the planets. As it accelerates towards the sun, it starts outgassing its volatiles. The tail forms. Ultimately, it's going to transform to a devolatilized nuclei. It's going to discharge all of that stuff that we see. Now we see 3i Atlas doing, right? So the fourth stage in the life cycle of a comet, disintegration. So now this cometary nucleus that aggregated in the first stage is now disaggregating, is disintegrating. We see vaporization of the icy matrix. So whatever material that's contained within that icy matrix, oftentimes silicate material, base material, is going to now be released into the orbital pathway, which then leads to the formation of meteor and dust streams after successive orbits. And the more it orbits, the more this material is going to disintegrate and produce ever more finer grades of material. Then finally, the amalgamation, which involves solar and planetary encounters, Planetary encounters can lead to crater formation on the solid planets, or they get swallowed up into gaseous planets like we saw with Jupiter. We saw the pieces of Shoemaker Levy 9 plunge into the Jovian atmosphere and essentially get swallowed up. Some of the plumes that came up to the surface in the aftermath of these impacts were larger than the Earth itself. So crater formation, raw material now that is produced in these hypervelocity impacts, right? You can now expose various elements to extreme pressures and extreme temperatures, and that material can now be injected into the atmosphere, into the hydrosphere, into the lithosphere. It can become part of the rock record because it's entrained literally into material that later on lithifies. The biosphere, okay? With all of these things combined, it then becomes the primary stimulus to extinction evolutionary cycles. So the biosphere is the area I want to look at when we start getting into exobiology, and how the accretion of cosmic material to Earth's biosphere may affect life itself. Not necessarily just in the extinction phase of the equation, but in the in the evolutionary phase. Is there a stimulus, a cosmic stimulus, that can accelerate that process? And if so, that raises to me very, very interesting questions, which I figure you're not adverse to exploring.
Never.
The possibility that, getting back to the Francis Crick model, which of course is beyond the scope of, I think, the discussion now, so let's not even go there. But I think that brings us up to meteor streams, which may be a good place to save for the next episode while we have enough time to look at some of your animations you've pulled together for us.
Sure, absolutely. So before we started tonight, we were kind of looking at a few different animations and trying to figure out how should we best provide a good understanding of what 3i Atlas looks like by comparison to a lot of our local comets and asteroids. So we went to theskylive.com and we pulled this up. Now, theskylive.com is a great tool. So let me pull up just a couple of comets that we're looking at. So we've got the orbit of 3i Atlas, C1995 Hale-01 Hale-Bopp, 1P Halley, 2P Enki, Hyakutake, and then Kohutek. And so let's pull ourselves back just a few years, back to
1975.
So you got Kohutek here, and then Hyakutake and Hale over here. Okay. And somewhere way out there we have 3i Atlas, not even on our radar. Then we have Enki. So I'm going to speed this up just a little bit. You tell me to slow it down when you're ready.
Okay, so I want you, look at there. Can you back it up? I want people to see how that tail twists around to point away from the sun as it's making its perihelion passage. Here it comes. Now watch this.
We're going to slow this way down.
Yeah, slow it way down. And you're going to see here the action of the tail. Here it comes.
So they're accurately representing what the tails always look like.
Yep. Look at this. There we go. Perihelion right there. And yeah.
So you were using an analogy before we got on of a dump truck
barreling down the highway.
A lot of people assume that the tail of a comet is going to be like trash coming off the back of a dusty, construction site dump truck.
Yeah.
But instead, you have the solar wind. The solar force is radiating out from the sun, And so the tail will always be opposite of that.
Always pointing in the opposite direction away from the sun.
Yeah. So it looks like Hayatake is getting a little glitchy there, but that's a highly elliptical orbit.
Oh, that's as I'm seeing, a purple orbit, and it's moving up to the left off the screen. That's Hayatake?
Right down here. Yep.
Wait, where's your cursor?
Right here, the red one.
Oh, there's Hayatake, and I can see that the red orbit, it's considerably tilted with respect to the plane of the ecliptic.
Correct.
Okay, so we call that in astronomical lingo, that's the inclination of the orbit. The inclination is the relative angle between the orbit of the object in question and the plane of the ecliptic, which can be defined very precisely if you just imagine that a line drawn from the center of the Earth to the center of the sun, that line lays exactly into the plane of the ecliptic. And as the Earth orbits the sun, imagine a huge rubber band connecting the center of the sun to the center of the Earth. And as the sun moves around, that rubber band sweeps out the plane of the ecliptic. And above that would be northern celestial latitude, and below it would be southern celestial latitude. So that's the zero plane. Right? So then the inclination of an object, whether it's a planet, whether it's the moon, whether it's comets, asteroids, the inclination is the measure of that angle, that tilt to the plane of the ecliptic. And the greater the tilt, that tells us that it's probably an Oort cloud object. Why? Because the Kuiper disk lays pretty generally in the plane of the ecliptic. So if it contributes a comet to the inner solar system, that comet is going to be within the plane of the ecliptic, which means it has a greater chance of being caught in that cosmic ping pong game between Jupiter and the sun, and then becomes a short period comet, right? As opposed to a tilted, highly inclined comet that is not bound in the same way, and its orbit can become much more eccentric, more flattened, right?
And so that's kind of the difference between two-eye Borisov and one-eye Oumuamua, that you have these high inclination of the ecliptic, hyperbolic in and out, whereas Atlas is hyperbolic, but it's within 5% of the plane of the ecliptic.
Yeah.
So that's where we're coming from, the perspective of, okay, it's on the plane of the ecliptic in line with the Milky Way. What are we seeing? We must be seeing something. So like the Kuiper disk versus the Oort cloud.
Yeah.
If you want to expand, if you assume that everything in the macro will come down to the micro, you assume that the Oort cloud and the Kuiper disk, there might be a similar analog
on the galactic
scale. Go to the galactic scale.
Yeah.
And so that's where, Randall and I were talking, perhaps we're seeing the Kuiper, part of the Kuiper disk body of interstellar bodies. Maybe
of the galaxy,
Atlas.
of the Milky Way galaxy, you're
Correct.
saying.
Of the galaxy.
Maybe. Well,
don't know.
We don't know. I don't know. I was hoping you would know and that you could tell me.
We have a sample size of 1. So
yeah. It's hard to extrapolate when your database consists of only one data point. So let's go back to the animation. We had, let's look at Comet Encke, because we're going to come back to that. There's a lot of discussion we need to have about Comet Encke, because number one, Comet Encke is part of the Taurid system. And that's the next major meteor stream coming up in October. So let's see, which one is Encke here?
Let's see if I can get us to get Encke. Encke's right here.
Yeah. Notice that as we're watching this, it's slowing down as it moves out to aphelion, which is the farthest point from the sun. And then it comes back in, starts falling in towards the sun, and it accelerates. Why? Because, well, the sun's gravity is speeding it up. Wow! It slingshots around. So you can see that elliptical orbit. And let's see, that's Anki. Where is Jupiter's orbit? Is that?
You're looking right here.
There. Okay. So check that out. So you can see how close Anki goes right out there. Doesn't have apparently enough energy to get outside the orbit of Jupiter. It's slowing down, and it's just going over the apex of the roller coaster ride, and now it's plunging back down towards the sun. Wonko, around it goes. So that's Anki. And Anki, again, part of the Taurid family, that we will definitely be talking more about that. Okay, let's see. And then there's Cahutek from the 1970. Notice how it really almost comes right into Jupiter's orbit, doesn't it?
Yep. It's right alongside Jupiter's orbit.
Aha. So it probably, I wonder where it was in 1973. But it's still out there. And what is its orbital period?
That I will have to look up. Let's see. 75D Cahutek orbital period. 6.66 years. How's that for
maybe that is why some of the religious nuts
maybe.
I didn't know that. Or maybe I knew it, but I'd forgotten it.
Yeah.
Interesting. Ooh, John. We better not go there.
We better not go there. That's something else.
Well, you do know that the orbital period of the Earth around the sun works out to be pretty much exactly 66.6 miles per hour, 18 and a half miles per second. I've done the math, 66.6 miles per hour.
There you go.
There we go. All right. So then we've got... what's the big purple one here?
You've got the hyperbolic here is 3i Atlas this year.
Okay. All right. Let's watch Atlas come through.
We'll back it up to 2004.
There it is coming from the top. We see it coming down. Here it comes. It's going to make. Here it comes. All right.
And let's kind of zoom in a little bit on Mars. So you're not going to see it all that close to Mars. I don't, so there are sites online saying that it's going to hit Mars. It could. Doesn't look like it yet.
Not yet, no.
So we're not seeing that at the moment. So could change. Mm-hmm. But this is going to be right around here is where we're going to have perihelion on the 30th of October.
Oh, okay.
And it's going to come out again. This is November. We're going to get a good look at it right along.
Oh,
here.
yeah.
This will be our best chance to get a good look at it. Late October, early November through November, when we're going to be out on the Azores tour.
Yeah.
With our good friend Darren. But and then let's see, it's come actually out to here because then in March. Let's bring it back right around the 20th, the 17th. That's where we will be able to see our closest passage to Jupiter.
Oh my.
Now, it's not going to be all that close, but it'll be close enough that we're considering. We just don't think that there's enough fuel on board the Juno probe, whereas the Europa Clipper, might be able to take good enough pictures from Europa. We might be able to get good enough pictures there and not compromise the mission. The question is the Juno probe has it's somewhere. Don't quote me. It's at least half or less the onboard propulsion that they feel that would be necessary to do a meet.
I see.
So it's significantly low, whatever it is.
So I'm wondering, with this proximity to Jupiter, is there enough gravitational force, tidal force from Jupiter to cause it to fragment?
We'll be a few million miles away, so
okay, probably not.
I think we're going to be good, but we don't know what this thing's actually made of.
Mm-hmm, right.
It'll show us what it's made of as it continues to outgas. The green gas, some folks have suggested is the cyanide. Normally, green would be a suggestion of carbon bonds, right, being broken C2, C3. But some folks have suggested cyanide so cyanide along with potentially nickel, but don't know. I'm not qualified to say if that would create that, but we have more studies that need to come out.
Okay.
We need to learn more. So, and then just playing it out of the system here. It's going to pass Uranus in 26, and it's slowing down on its way out. So it definitely picked up some speed coming in.
Yeah.
We'll leave the requisite jokes about that celestial body alone.
Sure.
The comment section will do that on their own, I'm sure.
So here we can see the difference between an elliptical orbit, which brings it recurringly back. Now it could be a long term, like we realize that Hale-Bopp, which is on a very eccentric elliptical orbit, has a return period of over 4,200 years. Right. And then we see Encke, which has a return period of about 3.3 or 3.4 years. Right. So there are vast differences. If we look at the orbit of Hale-Bopp, which one is Hale-Bopp?
Let me pull up Hale-Bopp. Hale-Bopp is down here.
Yeah.
Just so you can get a good idea of that.
Yeah. So notice how it's tilted steeply to the plane of the ecliptic. Inclined, should we say, and its elliptical shape is highly eccentric. So its major axis relative to its minor axis is high, is great. So it takes over 4,200 years for Hale-Bopp to make one orbit around. So I'm guessing Hale-Bopp was not originally a Kuiper disk contribution to the cometary population. Probably came in from the Oort cloud because, again, that high inclination is inconsistent with a Kuiper disk source.
Something likely perturbed it out of its orbit on the far edges of the solar system's gravity, and now it's moving.
Yeah.
It's a 2I Borisov and Oumuamua, hurts to say. Yeah. So the Scout, the first messenger, probably also, if you want to carry that model, which maybe not, could be. You see the Oort cloud, you see the Kuiper disk. Mm-hmm. You might just be looking at messengers or members of a larger body, interstellar body, similar to mirroring on a macro scale,
almost
the
like
Oort cloud.
Fractalization of a some type of an organizational structure on a larger scale. And if I was thinking along those lines, I would conjecture either further and think in terms of a subgalactic scale. There could be some order that still is beyond our field of purview, and then possibly on the galactic scale. There could be an intermediate. Thank you. That was the word I was looking for. An intermediate system of organization. And there might be some tantalizing evidence suggesting that as a possibility.
We need more data points before we can extrapolate. If we try to extrapolate off 1 or 2 or 3 interstellar objects, it's pure speculation. But I'm curious. It has me curious. What do these structures say? Do they rhyme with sacred geometry? Do they rhyme with the atom, the formation of the atom? Do you see this Russian nesting doll of concentric structures that mirror each other? What does that say for engineering, for science, mathematics?
Yeah, and these are all topics which I think we will be exploring, because I actually have some material on it. I have no definitive conclusions, but some very suggestive and tantalizing relationships that we see from the microcosm to the macrocosm and everything in between. In other words, I would say that what it sounds like you're suggesting is that it's like a fractal universe.
To an extent, sure, maybe. Hey, Avi Loeb is saying aliens, maybe, but also I'm saying if it's not aliens, maybe we're starting to see part of the structure of the universe that it just tends to follow a set of universals, and not as a hard rule, but if things tended to line up to a set of universals, there'd be some sense in it. There'd be some design in it. I tend to believe that there was a design.
Well,
so it's curious. It's curious. I'm making no claims.
Sure.
Purely speculating.
Well, certain fraternal organizations refer to the grand or the great architect of the universe. I'm going to pause for just a minute to talk about our partners over at Shippo, who may save you a significant amount of headache in your day-to-day business. We sell a variety of geometry tools and models, like our beautiful platonic solids here at Randall Carlson LLC. And when it comes to managing shipping, e-commerce, and returns, we've been using Shippo for over 4 years now, and we're very pleased with their service. Shippo's interface is intuitive, the primary order page is easy to navigate, and we have enjoyed stellar technical support. If Shippo can help you with your needs, please use the code below to partner with a great company while supporting our work here at Squaring the Circle. Thanks, and now back to the show. And then Comet Hyakutake, taken by Shigema Numazawa from Niigata, Japan, March 20th, 1996. Interestingly, 1996, both Comet Hyakutake and Comet Hale-Bopp were in the sky at the same time. Comet Hyakutake was discovered, I believe, after Hale-Bopp, but then came into prominence in the night sky to visibility prior to Hale-Bopp, I believe. I don't remember now. I was out there watching them both, but gosh darn, this was what, 30 years ago? 29? Let's see.
Yeah.
Yep.
29 years ago.
Seems like it was a few months ago. Just okay. But before we move on from Hyakutake, there's something that I think is of tremendous relevance to Hyakutake, and that is that there were high concentrations. The volatile discharges were showing high concentrations of methane, ethane, and acetylene, all which are highly flammable gases, which leads us to some interesting possibilities to ponder if you have encounters. Let's say, what happens if an object with high concentrations of flammable gases were to, let's say, do an aerial burst or a direct impact? That's a question not to be addressed now, but one that we'll come back to. I think that could have some important relevance. And then we had Comet Swan, discovered March 25th, 2020. Look at this, discharging an estimated 2,866 pounds of water every second. That is close to 1.5 tons of water every second. That's a lot of water coming off this thing, and that must be what's forming this incredible tail coming off of it here.
So in comparison to 3i Atlas, you're looking at mostly water as an exhaust here. As
here,
opposed to
this with Comet Swan.
With Comet Swan.
Okay.
Whereas 3i Atlas is an 8-to-1 ratio. So
right.
Not entirely foreign to the concept, but very different in the genetic makeup, if you will.
Mm-hmm. Mm-hmm. Comet West. This was back, I remember Comet West was just in the days when I was first noticing comets and thinking they were interesting. I think what really initially launched my interest in comets was Comet Kahutek, which I think came through in 1973, and there was all kinds of apocalyptic predictions about Kahutek, which did not, of course, come to pass. Just for fun, look up Comet Kahutek. I know we didn't program it into the animation, but it must have come, as I remember the hysteria surrounding it, it must have come relatively close to the Earth.
1973 came 1.4 astronomical units.
From the sun.
From the sun.
Now the question is, how close did it come to the Earth? Because, again, if the Earth was on the opposite side of the sun, you would have to add an astronomical unit to the distance. If it was on the same side of the sun, you'd subtract an astronomical unit.
0.8 astronomical units.
0.8. Okay. Well, in the cosmic sense, that's close.
It's close.
But not enough to get in a, panic over. But people were panicking over Kahutek. I do remember that. And I think that there was some, who was it? There was one guy, I think, who was kind of in the forefront. He was a recognized religious leader at the time.
So 100 years from now, how will our great-great-grandchildren remember 1973? In a future age when the names of Nixon, Brezhnev are dimly remembered, those of Irvin and Mitchell and Dean are minor footnotes in scholarly treatises. The name and discovery that will illuminate 1973 will be Lobos Kahutek. That's a quote from William Safire in a New York Times article named Kahutek's Comet, and Lubos Kahutek was the discoverer.
I see. Well, I would say that prediction
flopped.
I think most people, we're probably reminding the vast majority of listeners here about the existence of Comet Kahutek in 1973. But what I do remember very clearly about it were there were factions who were, and of course this is long before the internet, but there were factions who were definitely convinced that this was the apocalypse.
It was the end.
That Comet Kahutek was the agents of the apocalypse. So,
oh my goodness.
And that was kind of, but it served the purpose of putting comets on my radar screen. I would like to mention that one of our original sponsors at Cosmographia, CBD from the Gods, is following us here to our new podcast, Squaring the Circle. As many of you know, I've been using their products for going on 4 years now, and having tried a number of CBD brands, CBD from the Gods seems the most effective for my needs, which is primarily as a sleep aid and as a remedy for inflammation and associated pain. I use both the oil and the salve. My wife also likes their products, especially the salve, which alleviates the pain in her hands, which is the result of working for years as an electrician. If you've been thinking about trying a CBD product and experiencing the benefits for yourself, give CBD from the Gods a try. To learn more and see their product line, check out cbdfromthegods.com. Any purchase of their products helps our efforts here at Squaring the Circle to realize our goal of making this world a better place. Thanks. So, you know, I bet it's been a fascination of mine ever since, even though the world didn't end. All right, well, let's keep going here. There's Hyakutake, early 1997. And Comet Machholz conjunct with the Pleiades. I love this photograph here. Now, the Pleiades are significant in discussing the Taurid stream. And I'm not sure what the orbit of Machholz is, but I'm quite sure it's not part of the Taurid system. And then we have Comet Linear. This is a nice graphic because you can see here the solar system. You can see the Earth with its moon right here. This is the green circle. And then we have Venus, which is inside there. That's the yellow circle. Then Mercury, which is this pink color. And then we see red is Comet Linear. And what's interesting about Linear, this particular Comet Linear, is it was observed to undergo a fragmentation. But notice how it's tilted quite a bit to the plane of the ecliptic. So this looks like it would be an intermediary between a short period comet, which is going to have originated from the Kuiper disk, and a long period comet, which is most likely a visitor from the Oort cloud. So what we're looking at here is the inclined orbit of Comet Linear. Notice here, here's the position of the comet on July 26, 2000. And you'll notice, and this is the thing to get firmly embedded in your mind, is the tail is pointed away from the sun. It's going to be parallel to a radial axis. All of the solar wind emanates out from the sun radially. And the tail, the gaseous tail of a comet, is fine enough in its composition, its constitution, that the solar wind can cause the tail to move, to extend in the direction that the solar wind, of the pressure of the solar wind, if I'm trying to say it here.
And that's what makes Three-Eye Atlas a little bit unusual, and it is stirring a bit of controversy, is that there is apparently a tail pointing with the solar wind, but now there's outgassing occurring on the front side.
On the front side.
Now, you and I were talking before we started this. If I had to guess, which is always a bad idea, but if I had to guess, if there was a gun to my head, my question mark is, do we have highly volatile carbon dioxide and other volatiles that are now being outgassed towards, just because we have a huge amount of outgassing?
Yeah.
That's my question. And
what that would suggest is that the coma itself, or the nucleus, is itself highly volatile.
Correct.
I'm wondering now, could we possibly see this thing fragment as it's making perihelion?
I think it's a real question that should be entertained.
Mm-hmm. And we're about to see some examples of fragmented comet nuclei here.
And someone pointed out in the comment section, they asked, what happens if it hits the asteroid belt? Or are we on track? Is there a chance of fragmentation just due to hitting something local? That's a real question.
Mm-hmm. Mm-hmm.
There's some potential that it doesn't look like it's going to hit Mars, despite what a lot of videos on YouTube are saying. It could. It's within the margin of error, but it doesn't look like it at this exact second. We'll see.
Well, in a minute here, we'll look at the Sky Live animations that you've put together for us. We'll be able to zoom in. We'll actually watch the thing zoom by Mars.
It'll be close.
Yeah. So, Comet Linear, since we've still got this up here, this is from the Astronomy Picture of the Day, August 11th, the year 2000. This is from the NASA site. It has a photograph here. I'll pull it up in a minute. Fragments of Comet Linear. And it says here for explanation, what do you call a bunch of comet fragments anyway? A flock? A covey? A swarm? I like swarm. I've always used the term swarm. Okay. The question is definitely relevant to Comet Linear C/1999 S4, whose nucleus apparently fragmented late last month during its first trip through the inner solar system. So we have a computer-enhanced composite image showing the faint stars as trails and the remnants of Comet Linear's nucleus as a flock of mini comets embedded in a cloud of gas and dust. So let's go on here. Let's see.
So you have flock, you have swarm. I'd like to introduce or propose another common taxonomy that's been used. A congress, a bunch of brain dead inert objects that cause damage in their wake. But that.
Well, now that certainly is apropos.
Yeah.
As we would say. Okay, before we look at the photographs, this is just sort of one of the models of a of a nucleus, right? That differentiate from coma. And you have you notice here the outgassing through the crust. You have a crust, and in a Halley-type comet nucleus, the long axis here is about, I believe, around 10 miles. So it's pretty good sized. But when you do a cutaway of it, it looks like this. And you have who knows how many mini comets embedded in a icy matrix.
And just to compare, because you brought up Halley is how many miles in diameter?
Well, I think along the long axis, it's around 10 miles.
So just so that we have a point of reference, it's between 5.6 kilometers is the current mean guesstimate for 3i Atlas.
Okay, which means about 3.2 miles, roughly 3.1 to 3.2 miles.
So it's large as far as what we've seen as interstellar objects. But it may or may not be as big as Halley's Comet.
Right. But as of this point, there's no precise determination as to its size, right?
Because it has a very volatile coma. It is outgassing, just like you see here, at a very, very high rate.
So the thing to keep in mind, though, is that if something like this decides to disaggregate, it creates a swarm. And I think it's now not controversial anymore that you can have swarms created by disintegrating comet nuclei. Now, if this is 10 miles, or even let's suppose I'm mixed up and it's 10 kilometers, not 10 miles, the long axis here would be about 6 miles if it's 10 kilometers. So how many of these mini comets could it release? Like, say, into a close grazing encounter with the Earth? How many of these mini comets could be released? Thousands.
By the way, 15 kilometers long, 9.3 miles, give or take, long. So 8 kilometers, 5 miles wide. You're right.
Yes, I was in the ballpark. We're close to 10 in round numbers, yeah. So it could be that the Taurid meteor stream is the byproduct of the disintegration of a comet. And in fact, a comet that's probably much bigger than Halley. So anyways, let's go here. Let's see. Here's Comet Swashman-Wachman in the early stages of disintegration during the spring of 2006. And you can see here at the tail is now actual debris is beginning to, the nucleus is beginning to break up. And let's see, I think the next slide. Yeah, so there's a close-up of the debris trail from Comet Swashman-Wachman. Now, the resolution of this doesn't really give us the ability to count, but we could be looking literally at thousands of mini comets, pieces of the nucleus. Now, of course, once the comet breaks up, it creates the swarm. Over time, the swarm, it elongates, it spreads out right around its orbital path, and eventually, after a long enough period of time, I guess if it lasted long enough, it would be more or less uniform in density throughout its entire orbit. But I have no idea how long that would take. It would be a specific comet and how close it makes perihelion passage. How does it come close to Jupiter, any of the other planets? Because all of those gravitational effects are going to have a role to play in the disbursement of the pieces, right? However, for a long time, it's likely that there would be clusters where it's higher than the background density. And so if you have an Earth-crossing stream, such as the torrid stream, obviously, if the Earth is crossing the stream during a period of time where the density is greater, then the possibility or probability of impacts increases proportionately, right? Likewise, if it's going through an area where the material is, widely dispersed, so you got plenty of space between these subcomponents of the disintegrated nucleus, well, you might get through with nothing but a meteor shower. Ah, look, a shooting star, but without a repeat of the Tunguska object. Now, I've said it with no proof at all. We don't know the origin of the Tunguska object of 1908, other than the fact that it occurred during the peak of the summertime torrids, and its radiant point, or the point in space from which it was emanated, was consistent with the radiant of the torrid meteor stream. Does that mean unambiguously that it was part of the torrid meteor stream? No, but in my mind, it puts a member of the torrid meteor stream as being the prime candidate for those two reasons. If you dismiss that, you have to just, people say, Nikola Tesla was testing a weapon. I don't think that that's necessarily the most parsimonious explanation for that event. I think that the eyewitness accounts and the evidence is all consistent with a cosmic impact of some kind, and very possibly a piece of a comet. And that would be an interesting subject to explore in depth if you're up for it at some point, because there's new information. I've talked about it quite a bit in different podcasts, but a systematic breakdown of it, I don't think I've really gone through that since the early days of cosmographia. And we could probably do an updated, a little tighter presentation of that material. And what we now know, because we've actually learned some things in the last 5, 6, 7 years about the Tunguska event. Anyways, what you see right here, you have a close-up of the debris trail of Comet Schwarzmann-Wachmann. And now here we go, comet linear fragments. So August 5th, this is taken with the Hubble Space Telescope. And here you can see the object is really beginning to disintegrate here, and so the pieces of the nuclei are beginning to spread out. And here you can see there's a dense cluster of stuff of varying sizes. Now, if the Earth was to pass through something like this, be hell on earth, let me tell you. And it would probably be a major mass extinction event. But luckily, it's not a common thing. However, it may be more common than has been previously recognized. And I think there's evidence that, encounters with cometary swarms are actually more common than we had imagined a few generations ago.
In something like 3I Atlas, if it's primarily carbon dioxide, volatiles, and then you have that chondrite with all the little rocks in the middle. Something like that gets close to the sun, starts to melt or volatilize, You could see something like this from an interstellar object like 3I Atlas.
This, I think, is an awesome photograph, because here you can see that the nucleus is broken into two very prominent pieces. We see that the second nucleus is further subdividing and creating a whole trail of these secondary pieces that have discharged off of it. It even looks here like, looks like some of this has been thrown in front. I don't know what the rotational period of Schwarzman-Walkman is, but, comet nucleus are rolling and tumbling, so it can throw stuff off ahead of it. And then, of course, we get to Shoemaker-Levy 9, cometary debris chain. Now this, a little bit of background, it was probably orbiting between the Sun and Jupiter for, who knows, millennia. And it was positioned just in the right place, in the right zone, so that each passage by Jupiter, if this is Jupiter, each passage by Jupiter's gravity field pulled it in closer and closer, right? Now Jupiter's moving, but it's tightening that ellipse so that in the next turn around the Sun, it's coming back and making this passage closer to Jupiter than the previous passage. We discovered it just after what was just perijovian passage, meaning it made this close passage by Jupiter and it was within the Roche limit. What is that? Well, that is the limit relative to any body, a secondary body, passing within the gravitational field of a primary body close enough that the gravity field of the primary overcomes the coherence of the secondary body and it begins to disaggregate. Okay? That's what happened to Shoemaker-Levy 9. It was one nucleus. It passed within the Roche limit of Jupiter's gravitational field. Look up ROCHE, Roche limit. And essentially the gravity of Jupiter ripped the nucleus of Shoemaker-Levy 9 into 21 separate mini comets. Although those mini comets were pretty substantial, as we found out, right? So now you get this string of pearls that is now occupying the orbit that one orbit previously was a single nucleus. Now, after something like 3 or 4 months of observations, enough of the orbital elements had been determined, in other words, the shape of the ellipse, the velocity of it, the inclination, all of the 5 orbital elements that you need to be able to predict where some orbiting object is going to be at a given time. You have to know primarily the shape of its orbit and its velocity and its proximity to objects such as Jupiter or the Sun that can accelerate or decelerate the velocity. And within about 3 months, I believe, 4 months, they had established enough of the orbital elements that they were able to fast forward that orbit and discovered that in the second week, I believe, of July 1994, the chain of pearls was going to be crossing Jupiter's orbit. But the interesting thing was that it was going to be crossing Jupiter's orbit at the exact time that Jupiter was there. So this created a flurry of interest. It was, at that time, the most watched astronomical event in the 20th century, while probably in human history. And it was kind of, I know that it was important because it really helped to convince skeptical astronomers and scientists that planetary impacts actually occur. And here we are witnessing firsthand an impact. We don't know, we have no statistical basis because we don't have enough data points. We've only got one observation. But let's assume that something like this, we have no basis for saying, okay, something like this happens once every 1,000 years, once every 10,000 years, once every 100 years. We don't know. right? We're going to guess probably not every 100 years, because I'm guessing going back to the days of Tycho Brahe and the invention of the telescope, if something like this had happened, within the last 200 or 300 years, we probably would have known about it, but I have no definitive opinion on that. Maybe we would have, maybe we wouldn't have. The point is, though, if it happened 1,000 years ago, we wouldn't have known about it. If it had happened 2,000, 5,000, 10,000 years ago, we wouldn't have known about it. So how do we even project when we have only one data point? We can't build any kind of statistical base with one data point. However, it could be a lot more frequent than we had imagined. And if I had to come down one way or the other, I would say this is probably quite a bit more common than we had imagined. Because nobody was even imagining 21 gigantic impacts into any planet in 1 week ever. Of course, so it was sobering to a lot of scientists and astronomers going, okay, well, here's a whole nother class of event that we have to factor into our thinking. Although, sadly, like so many of these things, these omens, if you want to call them that, these messages from on high, the handwriting on the wall, whatever you want to call it, gets lost in the noise of everyday stuff, gets forgotten. Who knows, right? So the people that were alive of college age adults back then were very aware of this happening, but so 94, so what are we looking at? A whole nother generation and a half of people have come up. I quite frequently ask people, with Shoemaker leaving 9, the thinking that, well, doesn't everybody remember Shoemaker leaving 9? Then I got to remember, okay, yeah, a lot of people under the age of 35 were not even here. Nobody's taught them about it. Nobody's told them about it. Nobody's discussed the significance of this with them. And so it's just not on their radar screens. So this is why I think it's valuable that we're doing what we're doing, because maybe we can put these kinds of things back on people's radar screens, because the fact that 30 years, 35 years have gone by and it's kind of dimmed into, the memory hole of the human species doesn't mean that it's not important. And that an event like this could be very important at some point for our future.
And although this particular interstellar object 3I Atlas doesn't appear that it's going to come within the Roche limit of either Mars or Jupiter, it's going to be orders of magnitude, it's going to be millions of miles away. It's still tight by astronomical terms. It's not to say that the next one we see in 5 or 10 years, we don't know.
And
we don't know.
Yeah, and one of the things I'm going to be very interested in, if we can discern this as it comes in closer to the sun, is the composition of it. I'm very curious about that. Is it a solid mass, or is it even like an aggregation of, like some comet nuclei are really more like rubble piles?
Well, and the presence of nickel and not iron is really interesting, because you're not seeing a whole lot of carbon-based volatiles. Normally, you have C2 and C3, like we read in the literature last episode that we did on 3I Atlas. But we're seeing just nickel unbonded to iron, which the best estimate that we have, I believe we read the paper last time, but nicarbonyl structures would be the best assumption, where it's this carbon nickel combination that's during the volatile outgassing, nickel is being released, which is very unusual. We've yet to see that before. It's a whole bunch of firsts. It's our first time. So as we see this new anatomy of a comet pass by, this new composition, it's going to be very, very interesting.
Yes,
it's going to tell us a lot about the inner systems of the Milky Way.
Right, because we assume this is coming from another star system.
Which
raises the question. We were talking earlier about what kind of forces, for example, could dislodge a comet in a quasi-stable orbit in the Oort cloud or the Kuiper disk, and cause it to begin this sunward journey. And What are the potential candidates? We were suggesting perhaps a nearby supernova, perhaps the passage of a star, or maybe like a dense dwarf star through the outer zone of the Oort cloud. What else? Perhaps some internal instability within the Oort cloud itself. I don't know. Perhaps it's been hypothesized that there is a phenomena that's been referred to as galactic core explosions. Paul Le Violet, I don't know, forget how to pronounce his last name, has written a book. I read the book years ago. He surmised that there was a regular periodic galactic core explosion. So maybe that's a possibility. I don't know. That would be something I'd like to reread his book because I've learned a lot since I read his book probably 15 or 20 years ago. And I'd like to revisit that. But yeah, so there are potential mechanisms that could cause this destabilization within the reservoirs of comets. What did you find for Roche limit?
So yeah, the Roche limit is the minimum distance at which a body, celestial body is held together by its own gravity, can orbit a larger primary body without being torn apart by the primary stronger tidal forces. So for example, if you have if you have this aggregation, as it gets pulled closer, the gravity of the larger body will pull apart the aggregate closest to the larger body, and then as it disaggregates, the gravitational field decays and is ultimately defeated by the larger body.
So two major forces. We're going to have the internal gravitational coherence of the secondary, the smaller of the objects. Then we're going to have the gravitational field of the larger object. And, of course, the strength of that and the ability to exert tidal forces onto the secondary is going to be how proximal or close the secondary is to the primary. But there is a limit. There's somewhere, and I'm going to guess that limit, that threshold, varies depending primarily on the strength of the gravity field of the primary and the internal cohesion of the secondary, the smaller object. So the Roche limit then is going to be on it's going to be a variable thing. It's not going to be fixed. Jupiter's gravitational field is going to be constant. But now an object coming through, I'm going to guess we could say with a high degree of confidence that a dense iron asteroid is going to have a different Roche limit than a friable cometary nucleus. But anyways, that clarifies what the Roche limit. And who was Roche?
Edouard Roche is a French astronomer who calculated this theoretical limit in 1848.
Wow. Okay. 1848. Interesting. I would have guessed a little bit more recent than that, but anyways. So here is a very nice artist's rendering of what we saw back in July of 1994. This is actually what we saw. We saw the string of pearls kind of just almost passing tangentially by the orb of Jupiter. But if we were able to shift our perspective around, we could have actually witnessed the string of pearls impacting Jupiter. And here we're looking almost like directly under the south pole of Jupiter. So it was like boom, boom, boom. And any one of these impacts would have been enough to destroy civilization on Earth. Any one of these 21 pieces hitting the Earth would have been a major extinction level episode.
Thank God for the Jovian influence on the solar system.
It really
takes a bunch of these.
Right. It just swallows them up and prevents them from colliding with the Earth. But on the other hand, the other side of the equation is it can rip these things apart. True. And Okay, we've seen that. Swashman-Walkman. Second generation disintegration of comet Swashman-Walkman, fragment B. So this is that secondary fragment, which is now undergoing a further fragmentation. So you have generations of from the initial nucleus, which disintegrates, produces a second generation. Those pieces can disintegrate. Eventually what you end up with is a meteor stream and streams of cosmic dust, like the Zodiacal Light. We can save that unless you want to look it up. Zodiacal Light is probably a relic of the Taurid stream. The Zodiacal Light. It's caused by sunlight reflecting off of cosmic dust.
So this is from earthsky.org. The zodiacal light is a cone of eerie light above the sunrise or sunset point on the horizon. It appears at certain times of the year when all twilight is gone from the sky. The best time to see it is around September or March equinoxes. And you'll need a dark sky. No moonlight can interfere.
Okay, so we've got September equinox coming up. Today is the 15th, so like a week from now. It might be worth getting out and trying to see this, because I don't recall if I've ever actually seen the zodiacal light knowing that that's what it was. I may have seen it in the past. You know, growing up there in rural Minnesota, I saw lots of things and watched the sky a lot, but, you know, saw the aurora borealis quite frequently. May have seen this, but that's impressive looking. So what does it attribute the cause of the zodiacal light?
People used to think the zodiacal light originated in Earth's upper atmosphere. They thought it was a meteorological phenomenon. Then scientists thought the zodiacal light was sunlight reflecting off dust grains that orbit the sun in the inner solar system, which it is. But originally, scientists thought maybe these grains were left over from the creation of our solar system 4.5 billion years ago, assumed, or maybe from comets or asteroids. Recently, they discovered that is not the case. The dust grains do trace out the path of the ecliptic, which is the plane of our solar system and the path of our sun in the sky. But it's also the path that Mars takes. Mars is home to fierce dust storms, which scientists now believe somehow escaped Martian gravity to create the dusty reflective light we see.
Now, that's interesting. Yeah, I mean, I'm going back to, I must have learned about the zodiacal light and what it was, decades ago, probably in the 80s. So at that point, it was probably from meteorites and comets was the assumption. So this idea that it was dust storms from Mars, that's a totally new thing.
So just looking at that, if you're on audio, you gotta look at this. The zodiacal light is just this. It's that beautiful haze you see in some of the best nighttime pictures. So this is just regurgitating what was said on the. Let's see. So they discovered via Juno some dust storms there. So
on Mars.
On Mars, yeah.
And then what led them to believe that the Martian dust could be what's causing the zodiacal light?
Well, they saw cameras on Juno saw debris impacting the probe, and so they actually have a dust cloud. Let's see.
And this was as it's passing Mars?
Yeah. So there's this dust cloud.
Huh.
And that's where they're assuming potential dust storms, because of the lack of atmosphere, could actually be ejecting.
Okay.
Interesting.
Yeah, very interesting. And then we've got, they're called Catena crater chains. Now, are these from primary impacts or secondary impacts? We did look at the crater chain on the moon, didn't we?
We did.
Previous episode that was from the two giant canyons emanating out from the crater.
We did.
Yeah, we did that. So was this a possible debris from the secondary debris, the fallback debris from a larger impact somewhere? Or my initial impression was this was something where you had a very closely clustered chain of objects, almost with very little space between them, coming in and just like a machine gun almost blasting. So there would have been only maybe a matter of a few seconds at most between the impact of the leading object and then the terminal object. You can actually count here. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like there would have been about 12 or 13 pieces here to form this one. And it looks like it would have been fairly young because you can see that it actually like eclipses this crater here. It looks like it is younger than this crater. Let's go to the next one here. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces perhaps. But this is, I think it would safe to conjecture that this chain of craters here was a singular event.
Something that probably hit its Roche limit, and as it was falling apart, scribbled across the moon with multiple impacts.
Mm-hmm.
Possibly.
Yeah, here's another one. What are we? It's hard to count here. 1, 2, 3, 4, 5. This looks like it could have like somewhere up near 20 pieces. Now, have things like this occurred on Earth? It's a question I'm going to show you, not in this episode, but as we come back, we're going to look at some evidence that leads us to believe the possibility that something like this has happened on Earth. Maybe even several times that we might be able to discern. So maybe we should leave it there. I think we've covered a good dose of information here tonight. And I know that you're going to be engaged for the next week, but we will reconvene the following week to record another episode. As always, John, I always end up with these things with a million thoughts, stimulated my brain activity when I should be calming down and relaxing and getting ready to go to sleep.
So it's my fault that you have insomnia.
If I'm laying awake with insomnia all night, I will most definitely be blaming you, John.
All right. Fair enough.
Okay, no,
but at least you're thinking about interesting things. What can I say?
That's right.
Right.
All right, John. Well, thanks for this stimulating conversation tonight and exploration into these most interesting matters. See you next episode.
Look forward to it.